So guys, this is probably my most in-depth video I've ever done, or most constructive video, also with calculations, and it's about the altitude of the sun. Everyone wants to know what's the altitude of the sun, right? And everyone seems to know the altitude of the sun, at least the number that NASA gives us, which is millions of kilometers away from us, away from Earth. But what altitude would the sun have if the Earth is flat? Not a ball, but flat. And this is easily calculatable. Okay. And you may ask how? If you have no knowledge, if you did not go to high school, this may be a tough one for you. But if you went through high school and then university or something, then it's easy. Just people don't ever apply it to flat Earth, because usually they were already pre-programmed to believe that the Earth is a ball, and the numbers that NASA official institutions give us are correct, right? So they never put one and one together. So it's for both people, for the ones who never went through this type of mathematical schooling, and for the ones who went through that. The ones who did not go through this will learn something, surely, about trigonometry, that's what it's called. And the others will already know these things, but maybe some light will turn up, right? Oh, well, that's actually true. You could actually calculate for yourself the height or the altitude of the sun. And this image here shows something that is being used in astronomy, and it's called azimuth or azimuth. And it has to do with the fact that from an observer who is looking at a star, everything is bound to perspective, right? You have a location. As an observer you have a location, and the star has a location inside a 3D space, right? So because of this, there's perspective involved in all of this. If, for example, you stand next to a tree that is very high, and you're looking up at the tip of the tree, the crown of the tree, at that single tree, and you're looking up, and that tree is actually, let's say, 3 or 4 meters away from you on a flat surface, right? On the ground, it's 4 meters away from you, but when you look up to the top, it seems like the crown is actually right above your head, like at your zenith, just like it is in this graphic. There is a zenith right above the observer. But that's not the truth, right? Because you know that that tree is at least 4 meters away from you on ground level. Yet due to perspective, the top of the tree actually looks like it's right above your head. So you see that according to perspective, our eyes are also being fooled a little bit on where things are in this 3D space, and how we perceive them from our location, because we do not change the location. And to stars, for example, we are very low, right? Stars are very high. It's like the tip of a high tree that is then coming right above your head, because it's so high, because it's so much higher than your eyes are. And then it seems like it's bending over the tree, right? The higher it goes, it's bending over you, and then you perceive it as if it was right above your head, when that's not the truth. Because you know that the tree is going straight up from its roots, right? If it's actually a needle tree, it goes straight up. It does not bend right over your head, but that's the way you perceive it. And the same with stars as well, celestial objects. If you, for example, perceive the sun right above your head, then that doesn't mean that the sun is actually right above your head. It could be that the sun, because of its altitude, is still maybe 100, 200, 300, 400, 500, maybe up to 1,000 kilometers away from you on ground level. I'm saying the true zenith of the sun, you know, the coordinates of the sun. So this is also called azimuth in a way, because you see that the star is moving along a circle, okay, that has the observer at its center. And because of that, you know, if the star would go back to ground level at where the word azimuth is, right there, if the star would move down here, then you see, okay, it shares the same distance, right? But what a simple observer, so to say, or an uneducated observer would assume is that the star goes down here, right? Because you look at the star is here, and you think, okay, it's going down there. And the same could be that, for example, the star goes down here, but it's perceived there. Okay? That may be because the star is so high up in the sky, right there, for example, that an observer, due to angles, will perceive it here, along this line. Because if you just elongate this line, you're gonna end up where the star actually is, right? And where its actual zenith may be. So it is actually not so simple to get your head around this, because usually you think, okay, you're looking at the sun or you're looking at a star, and that's where it is. And it's true that that's where the light is coming from, but we want to know where are the coordinates within that 3D space of the zenith of such a celestial object. That means, where's the point here, right, on this field? Is it here, is it there, or is it here? Although we're looking at the star right there with this angle, where is this point? Okay. That's just something to know about. Now we're getting into how to simply, or break it down simple, without considering refraction, for example, which is another thing if you have never heard about it. Refraction is the thing that magnifies objects in the sky, because the light is traveling through a medium such as air, and it's a layer of air, especially at sunset, for example. Then the sun is magnified, right? We all know that when we perceive the sunset, that the sun seems to be bigger than during lunchtime, because the layer of air is magnifying the sun, or the size of the sun, because the light is traveling through lots of air, and that is called refraction. But we do not consider refraction in this example. Why? Because we're not measuring any angles in these positions, such as sunrise or sunset, in these crucial positions, so to say. But there is one crucial position, which is the zenith, which is very convenient to use, because we're looking at the sun with a very less amount of refraction of the air, because the angle is different, right? It is at its zenith. Okay, so for example, here is the sun at its zenith when we're looking at it, and here is the perceiver, here is the sun at its zenith. Here it would be sunrise, here it would be sunset. So it's convenient to use it here. But back to this. This is the way you can calculate from wherever you are, basically, and if you have a friend, a second person or something, the way you calculate also heights of trees. in the woods, for example, you can do this trick, so to say. It's a little trick that you can do. You just use trigonometry, you use some mathematical calculations, then you use some angles, and then you can calculate how high is the tree actually. You're looking at the top of the tree and you want to know what is the distance from ground to the top. Okay, and we're also not considering the height of the observer or anything that is linked to the way we perceive the tree. Because also what you have to say, if a tree is far away from us, then also what we would perceive the tree to be is lifted up a little bit from the ground, because everything that is underneath the eyes is ascending towards the horizon. So the roots of the tree and the trunk, where you can where the trunk is buried into the ground, this part will be slightly ascended to your perception. Okay, not in reality, but to your perception. We're not considering all of these things. So first, you are at point A and you're looking, that's the line, you're looking at the top of the tree, and then you can measure an angle. There are devices for this. For the sun, this is called sextant. Okay, this is what was used for a long time by sailors, for example, and still in use. If sailors like to go the old school way, then they can still measure angles with a sextant. By if that there was the sun, then they are measuring angles here. Okay, because they're looking at the horizon, which is basically flat. Okay, and then they're measuring this angle. The same you can do in the woods with a tree. And then from there, you maybe walk 150 meters, let's say this is meters, to point D in a straight line to the object. And you're measuring again, because now the angle will have changed because you got closer to that tree. So you look again at the tip of this tree. You measure another angle that is higher than the first angle. Okay, makes sense. I don't have to explain this why. And then what we do not know is the distance between point D and the trunk of the tree. Okay, the position, the location of the tree. You do not have to know this. The values that we know is this 150 meters between A and D. That's the distance that you measured, right? You went from A to D. Maybe you had a step counter in your pocket, or you have a ruler with you, or whatever you used to measure this distance. It's possible, easily possible. Then here you measured one angle, you have another angle here, you have three values to determine the height, and that's enough. And if it works for a tree, the height of the tree, then it also works for celestial objects, assuming that the Earth is flat, just like in this example. Here the surface is completely flat. That's what you assume, because if objects are close to you, obviously there is no curvature involved, except you're making some artificial curvature or whatever, you know. But in the most cases, it's flat. You can do the same with a mountain top. And what we're using for this to calculate, now getting into details, is trigonometry. Okay, for example, people know it also under the name of Pythagoras, Pythagorean theorems. And for this one, we don't care about sinus, we don't care about cosinus, we care about tangents, or the tangent. And the tangent is summed up in this formula, which is A divided by B. Okay, is the tangent of the angle at A, which is here. Okay, here is an angle, that's point A, here is an angle, that's A, that's B. So A divided by B gives you the tangent of this angle. That's the theory. And A is the side opposite, and B is the side adjacent. I don't know how you say that in English actually. but you know what I mean. So that's the basic calculation right there. I'm gonna go into further detail later on with an actual calculation, not here, just follow along. What I did is calculate the whole thing. You can see the value that you get. I wanted to zoom in. The value that you get for the height of the sun when you put everything into calculations is this value. The height or the altitude of the sun according to a simple idea, which is that the earth is flat and we're using trigonometry to calculate, or the tangent to calculate the height of an object having two angles. Then that's the value, 3779.44 kilometers. So that's the value for the altitude of the sun, just assuming that the earth is flat. You have a value of 3779.44 kilometers, and in miles it would be a little bit less, because we know that 3 miles are also 5 kilometers, so it would be around maybe 2000 miles if that calculation is true. Okay, so just bear in mind, even though you cannot go into much detail right here, or maybe pause the video and you can follow, but I don't know if you can read my handwriting here, but we're gonna go for a calculation later. So just assume that that's the actual height or the altitude of the sun. If we're dealing with a flat earth, flat surface, that's not high at all, right? If you think about, I mean, it is still high to us, but if you think about the values that we know from the heliocentric model, which is in the millions of kilometers, almost light years away, you think like you could never reach it, but almost 4,000 kilometers, that's like from Italy, I don't know, up to Sweden, or maybe a little bit more, right? Maybe you know a better example for what could be 4,000 kilometers of distance on ground level, right? Altitude is a different thing, because we cannot go too high. We can only go up to 100 kilometers, okay? So 3,000 or 4,000 kilometers of altitude is still high to people. Okay, none of us can go to these altitudes without lethal consequences. Okay, so this value actually makes a lot of sense if you know anything about astronomy. So now I want to get into detail how I actually calculated this. I want to walk you through this so you can do it for yourself. Okay, I'm not claiming that this value is true, but according to the calculation, simple calculation, assuming that the Earth is flat, looking at a celestial body, measuring the angles, and having a distance between point A and point B, is this idea here shows and demonstrates that it's possible. We can actually calculate the altitude of the sun according to a flat earth. Okay, but one has to assume that the earth is flat first. Usually that's not what people do. They went through high school system teaching, right, mandatory school, university. All they know is that the earth is a ball, it's heliocentric model, you know, and they never put one together. So I have these values from a source, and what you want to do is you type in to Google, search solar information or solar data or sun coordinates or the angles of the sun, and I'm gonna give you the link to this website later also, but for now just know that you can easily find these things through Google. A quick Google search can find you the data to this. And what data is important, I did it with one location, which is Berlin. You can choose any location of your liking, okay, wherever you live. And what is happening here in this website is it's giving you all the data from sunrise to its zenith to sunset, the time of this, okay. Times are here: dawn, sunrise, culmination, that's the zenith, sunset, dusk, and it gives you the times, okay. It's very convenient, but we do not actually need the time here. What we need is to know, okay, we're gonna go to culmination. We click culmination, okay, in this particular website. We click culmination and the sun jumps here. What we want to know is the angle from the observer to the sun. And when you go over to this again, you see that altitude, it's giving you the angle here, not the actual altitude in meters, kilometers, or anything. They give you the angle, okay. They don't want to make it too obvious. Of course, they actually say the distance here is in the millions. It's 150 million kilometers. That's the value that they give without any calculations or anything. But here at altitude, they tell you, okay, that's the angle. And that's measurable. Everyone can measure this angle actually. They cannot fool you with this. All they can do is fool you with this because there is no calculation attached or anything. That's just an assumption here. So what we want to know is, okay, these angles are true. Anyone can calculate them from Earth. They cannot fool with you. So what happens if we put these angles that the website also gives us into the theory from before that works out with trigonometry, okay, where you have two angles and then you're measuring the height of this object, okay. So you have an angle here. That's the first value that you save, 49.6 degree. Next thing you need is a point B, okay. As in the very first theory with the tree, we're basically walking to this point here. In reality, you won't make it in reality, okay, walking to this point. It's more than 100 kilometers, okay. So what you want to do is maybe you have a friend here in this location who can measure an angle. Or you go back to this website and you distract the second angle, okay. You do the same thing, you click culmination, the sun jumps here, and you get an angle right there, which is 51.16 degrees or 16 degrees, okay. That's the angle from here. And as I told you before, the second angle has to be bigger than the first one. And is that true? Okay, a quick check tells us, okay, the first angle is actually beneath 50 degrees, the second angle is actually above 50 degrees. Okay, so we can already say, okay, something is correct here. These are the two values that we want. And back to the distance between point A and point B, I used a distance calculator. Also type it into Google. You can find this. I'm gonna give you also the link to this. And what you want to do is just mark a point. It could be even further if you want. Just mark a point that aligns with Berlin longitude, okay. Also another point here is that it gives you the longitude here, okay, latitude, longitude. We know it's 13 degrees and 24 minutes 41.17 seconds. What we want is a location that aligns almost with 13 degrees and 24 minutes, okay. So what we do is we go down here, choose a point, and we look. Okay, now from the screenshot you don't see it, but I did it. You look at the coordinates of this point and you find out if it matches the longitude of 13 degrees and 24 minutes, okay. And then that's how you choose point B from a website, because you cannot possibly move as quickly from Berlin to this point and still have the sun at its zenith if you want to do it completely analog, right? But we're doing it digitally, and there are tools to do this digitally, and that's what I'm explaining here. So the distance is 173.69 kilometers between point A and point B. That's what I calculated through this website, and it's close to correct, okay? So with these values, I calculated the altitude of the sun. 3 values. You have the first angle, which is 49.6 degree. You have a second value, which is the distance between point A and point B. And you have a third value, which is the second angle, 51.16 degree. And with that, with this information, I calculated the height of the sun according to this idea right there. Okay, just my little scribble here. This is Berlin, this is the second point. I had a value here for the angle, I had a value there for the angle, and then I calculated the height using the tangent. Okay, and then I got the height of the sun. And as well, if I wanted to, I could actually calculate x as well, which is the distance between the second point and the zenith of the sun, the coordinates of the zenith. Okay, and I did that right there. Okay, so you have this value, and I think I already added it. Okay, it's already from Berlin to the sun. That's the value. Okay, so you have point B to the sun matches almost the altitude of the sun, the kilometers I'm saying. Okay, you see, so again, this is good, because that shows it makes sense, at least in the theory. Okay, these values are correct. And here is also the image, typing it in from Berlin to this point. That's where the sun is, above this region here. Okay, and it goes from east to west, and it matches, okay, with actual observation. The sun is around this point. The Tropic of Cancer is a little bit higher than that, okay, and we are at springtime, so it means the sun is still a little bit below that Tropic of Cancer. Okay, so it also makes sense. When the things make sense, it's good. You see that? That's the Tropic of Cancer. That's the line. And our value here almost hits it, right? Because we're approaching summertime. So also what we have to know is that all these calculations, any mathematical calculation, is actually just a nearing towards the truth. Okay, there is almost no mathematical calculation that is actually true, completely true. Okay, it's just a nearance. If you're working with wood and you're constructing a chair, then it's something else. But if we're talking about astronomy, about these things, right, it's a nearance, or very large distances, or maps, you know. You cannot possibly lay out one ruler to measure a distance. So there are things that we use, tools we use that work in the microcosm, so to say, 1 meter, 2 meters, and then we're just scaling it up, right? So it's just a sort of a nearance towards reality when it comes to these distances, right? Also something to keep in mind. And these are the sources that I used. For the solar angles, I used this suncalc.org, and for the distance calculator is distance point or .to. Very simple. If you have a good memory, simple to memorize. So why would we assume that the Earth is flat? Because just recently NASA gave us an image in the course of the solar eclipse. What is a solar eclipse again? The sun is in the sky, and at some point there is a shadow cast upon the Earth, which is coming from the moon, because the moon is coming in between the sun and the Earth. Okay, the moon is moving in front of the face of the sun, so to say, and blocking the sunlight. And some people in this world can witness this. Not all the people, of course, but some people. And this is the image that NASA released officially. Okay, so you have a pathway of this solar eclipse, and it's the shadow that is coming from the moon hitting the Earth, and there is this deep dark type of shadow, okay, which is this part. And anyone who lives here will have witnessed the solar eclipse. Anyone who lives here will have witnessed the solar eclipse. Simple, truthful observation. NASA cannot mess with this data because there are people living here and they are waiting for the solar eclipse to happen if NASA says that the solar eclipse is happening here, right? If this would not be true, these people living here, waiting or expecting the solar eclipse happening here that day, will mistrust NASA if they release any false data. So they cannot mess with this information. This is where you get the actual truth from NASA. But NASA does also release untruth, okay? Especially when it comes to things that people cannot reprove immediately, such as graphics, videos about moon landings, you know, all these films where people have no reference, okay, in reality. But here they have a reference because the solar eclipse is happening to anyone on Earth, okay? People from NASA cannot mess with that. And why is this important? Or why would I say, why would we assume that the Earth is flat, or is at least not a ball in the heliocentric sense, in this model kind of sense? Because this does not align with a ball theory and a heliocentric theory. This pathway here. According to a ball, the pathway of such a solar eclipse has to be there. Okay? Going from east to west. That would be the actual pathway of a solar eclipse. Or maybe here. Or maybe there. But never like this. Diagonal. Why? Because we know that here is north, there's around here is south, okay? And that's gotta be the axis of the ball, okay? From north to south, that's the axis of the ball. If day and night is created by the Earth turning around its own axis, if the sun rises here, it sets here, then the Earth must be turning from here to there, counterclockwise, so to say. Right? Around its axis. If that's the axis, it's turning right there. So, if the sun is making this movement, so to say, going from east to west, then the moon does the same. Because what is a solar eclipse? The moon is just positioned between sun and Earth. So if the Earth, no matter its tilt, is rotating around its own axis, that's gotta be the pathway. Just like the sun has this pathway, okay? We're witnessing the sunrise here, we're witnessing the sunset there. Pathways going there, okay? If there is a solar eclipse happening, meaning the moon comes in between sun and Earth because it's a new moon, then the moon does not really move. What's moving is the Earth rotating according to its own theory, right? According to the heliocentric model theory. So it has to move that way, the pathway, this shadow. So if this is truthful observation, and they cannot mess with this data, we know that the ball theory is wrong. At least in the heliocentric sense. Not saying that the Earth cannot be a ball at all costs, you know, but in the heliocentric model, this is not true, because in the heliocentric model, this has to be the pathway. One must think, are these maps incorrect? If this is not north and this is not south, because what we truthfully observe is this, right? Are these maps correct, or is north and south correct? Because according to this truthful observation that the shadow is passing by here, south will be there, north will be here. That would be the actual axis right there, okay? But according to maps, that's the axis of the ball. But according to this image here and the shadow passing by there, this is the axis. And I'm going to show you with the ball. If we assume that that's the Earth and it's a ball, and that's the equator of that ball, okay, doesn't matter if it's tilted, it could be this the equator, right? Then because it's rotating around its axis, if that's the axis, okay, going from here to there, and that's north and that's south, and it's rotating like that, and the sun has a point here, right? The sun is pointing right there, but the shadow of the moon may be hitting the Earth here, right? Because it's in between sun and Earth somewhere, the moon, so the shadow would be hitting there. If the sun is hitting right there, the moon's shadow is hitting there, and the Earth turns around its axis, you see what value you get? It stays there. It stays there. What does it mean if this axis is tilted? America is also tilted, okay? We go back to this, here is north and here is south according to the maps, okay? If we take this map and we put it onto this ball, then here would be north and here would be south. But if Earth is tilted that way, here is north and here is south, then also America somewhere here must be tilted to the right. So if according to the theory it does not align with what actual observation, truthful observation gives us, meaning that the solar eclipse pathway runs through these cities here, then something is wrong here, and we can assume that the Earth is flat. And it's not a ball at all. We can assume these things. And here you have a rotating ball, right? You have America here. If this is north, this is south, America is not tilted, okay, in this example. You see that here is a light spot coming from the light source, hitting it right there. Okay, you're gonna see it very soon, much clearer. Here is a light spot. It does not, the light spot does not change. That's static, okay? Here again, it's moving across from east to west because the Earth is turning. The sun is not moving. And if the moon is between the sun and this particular day creating the solar eclipse, also the moon is not moving, it's just the Earth turning around itself. And it will have a latitude. The shadow of the solar eclipse will have a latitude. And the pathway of the shadow of the moon would be here, in this altitude, or its latitude actually. And the shadow would follow along the latitude, okay? Just like the sun has a latitude, which will be soon the Tropic of Cancer right there, also the shadow of the moon, which may be a little bit above that, has a latitude of its own. If we assume that here is north, here is south, and the ball is turning around its own axis, and that's all, okay, it's creating day and night according to the theory. Going back here, it does not align with truthful observation. The shadow should be here. And if you were in Washington or somewhere, and the shadow is starting in New York, then you would get also the solar eclipse visible here according to maps. But it's not working. It's not working out. Okay, so we can say that the theory or the heliocentric model combined with the ball is not really true. Because according to the theory, I explained to you now, I think enough, it's not working out. Okay, again, you have the light spot here. The red dot is the shadow of the moon now. Okay, what does the shadow of the moon do? Nothing else. Okay, then being on a latitude while the Earth is turning. Yet, this is truthful observation. Okay, so now you have to say, okay, is this north? Is this south? Okay, then, because then the ball would turn around its axis again like that. Then this can be true, but then north is here and south is there, and not here or there. Another thing about flat Earth is when you get into perspective and what it does. How things are vanishing because of perspective and not because the surface is curved. It's possible that things are just vanishing because of perspective and because of the lack of visibility. For example, our eyes have a static field of vision. We cannot zoom like a camera can or a telescope can. And even if you can zoom with a telescope, there's a limit to that. First of all, there's a limit to zooming of a telescope, and secondly, there's a limit to the horizon, because the telescope is at a certain altitude related to its surface. So there is a natural border or barrier, which is the horizon line. And you see here that the horizon line is perfectly flat, okay? It has a certain level, which is sometimes 2.5 kilometers, 3 kilometers, can be different in different locations, the altitude of this bottom here. But that's the altitude, up to, in Europe or America, up to 3 kilometers. And you see that according to perspective, this bottom, it seems like it's bending towards you, while bottoms down here are almost not visible anymore, right? And it feels like it's sort of going like that, right? Like there's also nearness happening towards the horizon here, right? Because these ones are right above your head, and there are angles involved. And at the horizon, what is happening here is a collapse of angles, so to say, of your field of vision. It also comes with angles. If you look there, it has a different angle than if you're looking here, right? And if you're looking there, the angle is sort of zero, and then this would be minus angles. Okay, so it all comes with perspective and angles. And a vanishing point. Here things are vanishing, you cannot see them anymore, because things are collapsing at the end of the horizon due to angles. It's basically angles that are vanishing things. As strange as it sounds, that's the way we perceive it to be. Obviously, these things in reality do not vanish in truth. They are not disappearing in truth. They are still there, they exist, but to our perception, to an individual's perception on Earth, not changing its location. Things are vanishing, okay, according to the perception. Just because we or an individual does not see these things anymore, doesn't mean that they don't exist, and it also doesn't mean that the surface must be curved, and that's why they are not there or visible anymore. That's another thing that people have to learn, that there is a phenomenon which is linked to perspective and angles, that is vanishing things. It's also called the vanishing point in drawings, pencil drawings, for example, when you're drawing a road and the city skyline or whatever. You're making use of the fact of perspective. Okay, when will people that learn this stuff in school put one and one together? And also, perspective does not mean, it cannot solely be used as a proof of flat Earth also, because perspective also applies to any shape, right? Because that's just how our visual works. There's perspective involved, and we cannot zoom into things. But one thing that people have to remember is that because ships are vanishing at the horizon doesn't mean that the Earth is a ball and that the surface is curved. Okay, it can also very well happen on a flat Earth due to perspective. And this should prove it. You find yourself on a road with a car and you're thinking, oh, you're approaching the sea very soon, the beach, but you never knew that there was a beach in your hometown, right? You may be living in the middle of America. Where does this beach come from? Or the horizon, the ocean? Did God bring the flood back or what? You know? And it's also written, this is a post on Instagram, when you think you've arrived at the beach. And what it truly is, it's the building of IKEA, which is blue. Okay, and because it has this flat rooftop, it's perceived as an ocean. Okay, so you can say that the same thing is happening with the ocean in reality. If that was ocean, then there would be a horizon line right there. Okay, and beyond that horizon line, you cannot see these things. In reality, this is the building of IKEA, which is blue, and it gives you the illusion of ocean, because that's what we associate this image with, right? The first thing we would think of is ocean, but when you have knowledge that this is IKEA building, you can see it also. This is the edge of the roof, and now this is a flat roof. Okay, can you see a bird, for example, that is standing in the middle of this flat roof? No, you cannot see it from this perspective. Okay, you're standing here, and this is how important perspective is, because you're looking at this edge right there. Anything that is beyond this edge, actually, if I want to draw it here, it goes like that. Okay, actually it's the other way around, sorry. It goes like that. Okay, can you understand that? If, for example, this was transparent, this wall would be transparent, then at the end you would see a transparent roof also. Okay, and the last wall would be here maybe. Okay, if you could see the other wall, it may be here, right there, a smaller thing due to perspective. So you see how things are actually moving down from this perspective. You have here an edge, and although this roof is perfectly flat, in reality we all know that when we go into IKEA, the roof isn't like dipping at some point. It's flat, okay? But according to this perspective, you perceive it only as this edge, and beyond that edge you do not see any objects that would be in the middle of this roof standing. It's just like a bird, or you could even put a car there. You would not see it from this perspective. And the same, if now a man is climbing up here, let's say somebody's cleaning the stuff, the wall, the facade here, is walking up here, it's just like a ship almost that is going up there. And then once this worker or cleaner has reached the top, he will probably climb the top and then walk on top of that flat roof towards the center and slowly disappear to your perception. And the same goes for boats. Okay, because they are moving beyond the horizon, you cannot see them anymore, because the horizon line is basically like the edge of this roof. It's flat, and anything that goes beyond that natural border, which is this water, then is also descending again, and that's why it's perceived to be vanishing or going beyond a curved surface, when that may not be the truth.